We're getting to more juicy things, and some things just cannot be computed by hand. And that is especially the case when you start getting into harder concepts such as calculus and discrete mathematics and something along those lines, higher math, so to say. And that is why we will cover all the topics related to calculus now with the following videos. I'd like to start with derivatives. How do we take a derivative in Wolfram Mathematica? To take a derivative in Wolfram Mathematica, let's say we have an expression sine d x squared sine of x, and we want to integrate it in relation to x. All we have to do is use this d function. As you can see, it's black, so it's in the black font, which means the Mathematica is recognizing the function. And the first argument is what we want to work on, our expression. And the second one, of course, is in relation to what do we take the derivative. In our case, we take it in relation to x. Just as you see, it's very simple. It just computes it. But there is another thing about the second argument, because we can take a third derivative if we want to, or 100th derivative. And all it takes is to add these curly braces, put the x as the first argument and 100 as the second argument, or whatever order of derivative do you want. You want 7th derivative, you put 7 in here. That's it. Very simple. Now, let's look at a different way to define or to do that operation. And a different way is to use the stick. The stick is differentiation, and the way you define the order of differentiation is that you just specify the number of ticks. That is, this is the first order derivative, this is the third order derivative. Very simple. And the tick and the d are equivalent. That is, there is no difference between the two. For instance, let's just define useful function f, right? F, x, and delayed set operator, x cubed minus 2x squared minus 5x plus 6. That's it. We have defined the function f of x, and now we can just use it. If we want to get the derivative of f of x, it's very simple. We can just get the derivative. And if we were to compare difference between the two, that is f of x, let's differentiate it in terms of x for with the d function, and then let's do the exact same thing but with the tick notation. As you can see, that is the exact same thing, there is no difference. And if you wanted to, you could take the third derivative as well. Let's just add 2 ticks in there, and yes, it's just 6. Now we can plot these different equations, and where the tick notation really comes in handy is where we want to plot the functions. In our case, we'd like to plot f of x, then first derivative and the second derivative. Then we would like to plot it on the interval from -3 to 3. And then we will say plot legends expressions, so we see what is what. And as you can see, f of x is the blue graph, the orange graph is the f prime of x, the first derivative, and green graph, or the linear function right here, is just f double x, that is second derivative of x. And this prime notation is really comfortable. when you want to use it with tables, let's say, and let's say the first value is x, next one is f of x, f of prime of x, that is the first derivative, second derivative is f prime prime x, and we want to take values from 1 to 10, that is the x will be from 1 to 10. And another thing is that we are going to pipe it into table form. And the reason we're doing that, I'm going to show you that in a couple seconds. Yeah, right here. Right now, nothing's clear, nothing's understandable. Now everything's in table form, as you see. 1, derivative of 1 is 0, like just f of x, then first derivative, if we put 1 into first derivative, we get 0. If we put if we just put 1 into f of x, we get 0. If we put 1 into first derivative, we get minus 6 right here. And second derivative yields 2 as a result of us putting 1 into it. And these are inputs. And every single row gets calculated just like that. Quite handy. Now, the D function also supports differentiation in relation with multiple variables. That is, you have differentiation, you have x squared, let's say cosine of x, let's add y in there, then plus y squared, then we have sine of x and y, and we will differentiate it in terms of x and y. And voila, it gets done. Now, the result of D is not always returned in the simplest form it can be, and that is the reason why, let's say, if we have sine of x to the 10th power and would like to differentiate it in terms of x, we need to use simplify afterwards. Let's take the last output, and that's it right there. Let's say x, let's take the fourth derivative, and now it's simplified. Yeah, this is a much more clear example. Another thing we can do is we can do derivatives of purely symbolic forms. That is, it doesn't have to be a number or some particular expression. We can just differentiate it as it is, and it will be used as it is. That is, gx is undefined. As you see, it's in blue, which means it's undefined. And x then is our variable in terms of which we differentiate. And as a result, we get that. Now, this is useful when you want to explain formulas or formal concepts. And after you have done that, let's say you take a second derivative of that, it does it, and once the explanation, whatever you wanted to get across to the user or your students, as long as it's done, you can then substitute. G with, let's say, sine if you wanted to, or tangent if you wanted to. Very simple. And that is practically it.